All right, let's talk about something we hear all the time, the greenhouse effect. It's this massive, fundamental system for our planet, but what does it actually mean, really? Let's get into it.
First off, I want you to just look at this number, minus 18 degrees Celsius. That's cold. And that's what the average temperature on Earth would be if we didn't have a natural greenhouse effect. We're talking about a giant frozen ice ball, pretty much lifeless. So what's stopping that from happening?
Well, that brings us right to our first section, Earth's natural thermostat. We're going to look at the basic, life-sustaining mechanism that makes our world not just habitable, but, a pretty great place to live.
It's actually a pretty simple process when you break it down into 3 steps. So, step 1. Sunlight beams down through the atmosphere and warms up the ground. Easy enough, right? Then, step 2. The Earth's surface, now all warmed up, sends some of that heat radiating back out towards space. This is infrared radiation, basically what we feel as heat. And here's the crucial 3rd step. Some of that heat doesn't escape. It gets trapped by certain gases in our atmosphere, which keeps the planet toasty.
And this is exactly where the name comes from. This quote from National Grid nails it. The gases act like the glass walls of a greenhouse. It's the perfect analogy. Sunlight gets in, warms the place up, but some of that heat can't get back out. That's what these gases are doing for the entire planet.
So let's be super clear about this. The natural greenhouse effect is not the bad guy here. In fact, it's absolutely essential. It's literally the reason we have life as we know it. Without it, the average temperature would plummet by 33 degrees Celsius. Our beautiful blue marble would just be a big white snowball.
Okay, so if the atmosphere is like a blanket, what's it actually made of? Let's pull back the covers and meet the specific molecules that are doing all this important heat-trapping work.
All right, here are the main players. You've got the famous ones, carbon dioxide, methane, and nitrous oxide. These come from all sorts of places, both natural processes and human activities. Then you have water vapor, which is actually the most abundant of the bunch. And finally, there are these industrial fluorinated gases. These are purely man-made, and boy, are they powerful.
Okay, but wait a second. You might be thinking, and it's a really good question, CO2 is just a trace gas, right? I mean, how can just 4 molecules out of every 10,000 in the air possibly heat up an entire planet? It seems kind of crazy when you put it like that. Well, the answer is all about how powerful they are, not how many there are. This quote gets it right. They act like a protective blanket. It's kind of like adding 1 drop of super hot chili oil to a giant pot of soup. You don't need a lot to feel the heat. These specific molecules are just perfectly structured to grab that outgoing infrared heat and bounce it right back down to us.
And this is where the conversation gets a lot more complicated. That natural system, that perfect blanket, works great when it's in balance. But what happens when we start adding more layers? Well, then you get what's called the enhanced greenhouse effect, and suddenly you can have way too much of a good thing.
You can see the difference pretty clearly side by side here. On one hand, you have the natural effect. That's what gives us a stable, comfy climate. But on the other hand, you have the enhanced effect. This is driven by our emissions, and it's like we're just piling on more and more blankets. It starts trapping way too much heat, and that stable system, it starts to get seriously out of whack.
And when you look at the timeline, wow, the numbers tell a pretty stunning story. For thousands of years, CO2 was just humming along at about 288 parts per million. Then, by 1960, it's up to 315. But look at that next jump. By 2022, it shoots up to 421 ppm. That is the highest it's been in millions of years. The speed of that acceleration is just incredible.
So what's driving this? Well, this chart makes it pretty clear. Of all the extra greenhouse gases we're pumping out, look at the big slice of the pie, carbon dioxide. It's responsible for nearly 3/4 of the emissions. It is, without a doubt, the main driver of this enhanced effect.
Okay, so how do scientists actually measure all this? How can they be so sure where this imbalance is coming from? Let's dive into the science of how they figure this stuff out.
They use a tool called radiative forcing. Now, that sounds super technical, I know, but the idea is actually simple. Think of it as a scientific measuring stick. It just measures how much any given thing, whether it's CO2 or a change in the sun's brightness, is pushing the Earth's energy budget one way or the other. Positive forcing means things are heating up. Negative forcing means they're cooling down.
And this right here, this is the crucial data. This chart uses that measuring stick to compare human impacts, that's anthropogenic, versus natural impacts. And look at the results between 1980 and 2011. The warming push from human activity is huge. And the push from natural stuff, like the sun and volcanoes, it's basically zero. The difference is just undeniable.
And this isn't just some fringe idea. The IPCC, which is the world's leading authority on this stuff, they say it with very high confidence. And in science speak, that's about as certain as you can possibly get. They're saying the natural stuff is barely even a rounding error compared to what we're doing.
So, okay, the blanket is thicker. The science says we're the ones who've been piling it on. But what's the big deal? What does this actually mean for us, day to day? Let's connect these numbers to the real world.
Well, the consequences of knocking this system out of balance are huge. I mean, the World Health Organization calls it the greatest threat to global health in the 21st century. They are not mincing words. We're talking about fundamental things, threats to our food and water, more flooding, extreme heat, new diseases, and major economic hits. The whole shebang.
And that's really the heart of it, isn't it? We depend entirely on this beautifully tuned natural system. It's what has allowed human civilization to flourish for millennia. But now we're pushing that very system way out of its comfort zone, and we're doing it incredibly fast.
So we're left with a pretty sobering thought. The debate isn't really about if the system is changing anymore. The evidence for that is just overwhelming. The real urgent question now is, how far can we push this system before it hits a tipping point? How much pressure can it take before the changes simply can't be undone? Thanks for tuning in.